Hi, welcome to Lecture 3. In this lecture we'll be talking about the echelon forms of a matrix, and we'll revisit questions from the previous lecture about linear independence and linear combinations. And we'll give answers to those questions. Okay, so first we have to mention elementary row operations. Okay, so elementary row operations are operations you can do on a matrix that doesn't change the important properties of a matrix, essentially. Okay, so there's three of them: replacement, interchange, and scaling. And I'll just give an example of all three. Okay. So if we suppose this is our A here, here's a replacement operation. So what this is you take copies of one row and add it to another row. So I'm going to transform row 3 here by adding -1 copies to row 3. Okay, and this is the result. Notice we don't change row 1 in this operation. We only change row 3. Another operation is an interchange, which is swapping two rows. So from this matrix here, which is this matrix, I want to swap row 2 and row 3, and this is the result. And then there's scaling. Okay, so scaling is when you multiply a row, every entry in a row, by some non-zero constant. Okay, so here we're multiplying row 3 by 1/5, and this is the result. Okay, so the purpose of elementary row operations is to put a matrix into echelon form. Echelon form tells us a lot about the matrix. Okay, so let's describe what echelon form is. Okay, so there are different kinds of echelon forms. Okay, so if a matrix has these first three properties, we call it a matrix in echelon form. Okay, if it has all 5 of these properties, then we call it reduced row echelon form. Okay, so reduced row echelon form is more work to get at than just echelon form. Okay, so to understand what these conditions mean, okay, it's helpful to look at a diagram which shows off the shape of matrices in these forms. Okay, so a matrix in echelon form looks like this. Okay, where the black boxes here are a non-zero number. The stars can be any number. And the important shape here is that the zeros form a staircase like this. Okay? And over here, we have this staircase. Okay, so that's the echelon form of a matrix. Okay. And then if we do a little bit more work to it, we can get it into reduced row echelon form. Okay, so here, so these black squares are leading terms. Okay, that's what they're called. They're the first non-zero entry in the rows, going from left to right. Okay, so in reduced row echelon form, or RREF for short, we make sure that these leading terms are 1. Okay, in addition, above each of the leading terms, we make sure all the entries are 0. Okay, so this is echelon form, this is reduced row echelon form. And also comment that the reduced row echelon form of a matrix is unique. Okay, so there's only one reduced row echelon form of any given matrix. The more general echelon forms this form is not unique. Okay, so if we look up here, our A, when we did these operations to it, we did this operation and then this operation, we actually got it into echelon form here. Okay, this is echelon form. Okay, and if we wanted to put it into reduced or echelon form, well, this step is one of the first steps. We have to turn this leading term into a 1, and then we would have to do a few additional replacements, where we use this third row to make this and this 0, and then we use the second row to make this 0. And then that would be the reduced row echelon form of A. Okay, so the reduced row echelon form of A is the identity matrix. Okay. And now I'll say some important definitions. So these leading terms, okay, so the leftmost non-zero entry in each row of a matrix in either echelon form is called a pivot. Okay, so I'll explicitly highlight the pivots here. So this is a pivot, this is a pivot, this is a pivot, this is a pivot, this is a pivot. Okay, so the echelon form reveals the pivots. This is a pivot, this is a pivot. Okay. The number of pivots in an echelon form is called the rank of a matrix. Okay, so the rank of a matrix reveals a lot about the matrix. It's probably the most important thing about the matrix. Okay, so for example, the rank of this matrix is 1, 2, 3, 4, 5. The rank of this matrix is 1, 2 pivots. Okay, same with these two. And the rank of this matrix up here is 3. Okay, so let's revisit our question about linear independence, how to determine if a set of vectors is independent or not. Okay, and with our new tool of echelon forms, we're able to answer that. Okay, so like I've mentioned before, it's useful to think of a set of vectors, v1 through vq, in Rm, as columns in a m by q matrix A. Okay, so we have our set of vectors here, and we can make a column, we can make a matrix, an m by q matrix, right? A, where the vectors are columns. Okay, and we want to be able to think about these two things interchangeably. Okay, so what was our question about independence? Okay, so given a set of vectors v1 through vq in Rm, how do we know if they're independent or not? Okay, so here's the answer. First of all, we want to form the matrix A, where we set the vectors as columns. Okay, and then we want to put the matrix A into an echelon form. Okay, then compute the rank of A by counting the number of pivots. Okay, if the rank of A equals Q, that is the number of column vectors, okay, then the set is independent. If it falls short, that is, if the rank of A is less than Q, then the set is dependent. You could think of being independent as a good property for vectors to have. Okay, just like a matrix being invertible is a good property to have. Okay, so suppose you have a set of vectors. Okay, you want to know, is it independent or not? So you do this method, you put in a matrix and you compute the rank of the matrix. Okay, so it turns out that the rank is less than the number of vectors, and so it's dependent. Okay, so the next question you could ask is, if I can't have a full set of independent vectors, what's the next best thing? In other words, what's the biggest subset or subcollection of these vectors I can have that's independent? Okay, and that's what the rank is telling you. Okay, it's the biggest set or the biggest subset of these vectors that can be independent. Additionally, the echelon form, the pivot positioning, tells you how to pick from these vectors so that you create an independent set as large as it can be. Okay, so let's work through an example that communicates these ideas. Okay, so this fact is recording what I just said. Okay, so if you have a matrix, these columns as vectors, when you put it into echelon form, the pivot positions highlight the largest set of independent columns of A. Okay, so now let's look at an example of that. Okay, so let's look at this set of vectors, S. Okay, so how many vectors is it? It's 1, 2, 3, 4, 5, right? In what space are they in? Okay, they're in R4. Why? Because each of them has 4 entries in it. Okay, so this is a set of 5 vectors in R4. That means we're going to form a 4 by 5 matrix A. Okay, so I form this matrix and I'm going to put it into reduced row echelon form. Okay, for a big matrix like this, you might want to use a calculator. Okay, so here it is, and I've circled the pivots. So we have 1, 2, 3 pivots. That means we have a rank of 3, right? So what does that say for the dependence or independence of this set? It says that it is going to be dependent, right? Since the rank is equal to 3, and that's less than 5, the number of vectors, that means that this is a dependent set. Okay, so as I said, the position of the pivots communicates how we can form an independent set of columns of A that's as large as possible and independent. Okay, so in the echelon form of A, notice the pivots are in column 1, column 3, column 4. Okay, so that's indicating to us that if I go back to my original matrix A, that column 1, 3, and 4 form an independent set that's as large as possible. Okay, so this set C of, I'm going to call these special columns the pivot columns of A. Okay, this set C is made up of my pivot columns, and it's an independent set. Okay, and the size of it is of rank, the size of it is of 3, which is the rank of the matrix. Okay, so what did echelon form do here? Okay, so we gave it a matrix with 5 columns in it, and it determined that these 3 columns are the important ones, and the other 2 columns, we'll call them the non-pivot columns, they can be written as linear combinations of the important columns, the pivot columns. Okay, so now I'll give you a nice upper bound on what the rank could possibly be. Okay, so let A be an m by q matrix, then the rank is going to be less than or equal to the minimum of m and q. Okay, by this I mean the lower value of m and q, where m is the number of rows and q is the number of columns. Okay, so that's an upper bound for the rank, the highest the rank could be. Okay, so why is this true? Well, it follows from the definition of echelon form. Okay, so echelon form only allows for 1 pivot per row and 1 pivot per column. Okay, if it has more than 1, then it's not an echelon form. Okay, so that means that the most the rank can be will be the lesser of the number of rows and the number of columns. Okay, so this has a pretty interesting consequence. Okay, let's go back to our example here. Okay, so what's the highest the rank could have been for our set here? Okay, since it's a 4 by 5 matrix, that means the rank could at most be 4, because that's the lower number, right? If you try to fit in 5 pivots into this, a matrix of this size, it just doesn't work, right? So since the most the rank could be is 4, that means this set of vectors never had any chance of being independent, right? Because it needs to have 5 to be independent. So just by the number of vectors and the dimension of the space it's in, we could have declared that this was dependent just by looking at it. Okay, so in short, if the number of vectors exceeds the dimension of the space it's in, it's always going to be dependent. Okay, so that fact is recorded here. So if you have q many vectors in Rm, and if q exceeds m, the vectors will always be dependent. Okay, so now I'll mention the definition of the column space of a matrix A. Okay, so let matrix A have columns v1 through vq. Then the column space of A is the span of its columns. Okay, in other words, all linear combinations of its columns. Okay, so this is the notation we use. We say, or we write, col A is equal to the span of the columns is equal to, so we write the form of a linear combination of the columns, and we say that its weights are all of the real numbers. Okay, so that's the definition of the column space. And I'll also mention that the pivot columns of A, the good columns that are highlighted by the echelon form of A, form a basis of the column space of A. Okay, and we'll get into basis later on, but it's good to note this now. Okay, now I'll mention another characterization for independence. Okay, so let's consider a set of vectors v1 through vq. Okay, so here's another way to think about independence. Okay, if none of the vectors can be written as a linear combination of any of the other vectors, then the set is independent. Okay? On the other hand, if at least one of the vectors can be written as a linear combination of the other vectors, then we say the set is dependent. Okay, so here are two examples of what I mean by one written as a linear combination of the others. Okay? So if one vector is a multiple of the other, say we have this relationship here that v1 is just 2 times v2, okay? That means we have dependence among the vectors, and that means the set is dependent. Okay, but it can be more than just a multiple, right? Suppose we have v3 is equal to 2 times v1 minus 5 times v4. Okay, so this shows that v3 is a linear combination of v1 and v4. Okay, so this set will be dependent as well.